So, welcome once again to the course Applied Econometrics, and we were discussing about dynamic panel data model, right? So, this is dynamic panel data model. And before we go into today's discussion, I would like to just recap what we have discussed in our previous class, right? So, why dynamic panel data is required? Because if you recall, we said that many of the economic relationships are dynamic in nature. For example, in the context of agriculture, when the farmer is deciding about how much land to be allocated for ith crop in tth period, that basically depends on previous year's production, because previous year's production would have resulted in some price followed by some amount of profit, and that will motivate the farmer to decide about the land allocated for the same crop this year. So, a heavy profit or huge profit for the ith crop last year may again motivate for the farmers to go for larger amount of land to be allocated for the same ith crop in tth period as well. And similarly, we have also discussed how in the context of a farm production, if the firm would have produced more in the last year and could not sell much in the market, so much of the production would have gone for inventory, and that will reduce the amount of production this year. Similarly, in the context of income for a country, let's say in India's income or GDP last year will basically determine what would be the GDP for this year as well. Many a times when you apply for job market, your employer will ask you what is your last scale that you used to draw in your previous organization. So that means while fixing your grade or payment in the new organization, your new employer will have a look on your previous salary. So these are all many examples that we can draw upon to show that how economic relationships are dynamic in nature. And how do you model this dynamic relationship? Just by adding the lagged value of your dependent variable. So that means we model dynamic panel data in this way: YIT equals to basically we said let's say this is beta 1 yi t minus 1 plus beta 2 xit plus ai plus vit, where ai plus vit is basically the composite error term, which is again is as uit. Okay, sometimes instead of using the coefficient beta 1, sometimes we use a different coefficient just for the notation sake to differentiate this variable with the other explanatory variable. So, let us say this is rho yi t minus 1 plus beta 2, or you can use beta 2 xit plus uit. And then we said that this dynamic panel data model, there is another name for this model which is called partial adjustment model. And to understand the why this is called partial adjustment model, then we can just subtract yit minus 1 from both sides of the equation. So, if we subtract yit minus 1 from both the sides of equation 1, what you are going to get is yit minus yit minus 1 equals to 1 minus rho yi t minus 1 plus beta 2 xit plus uit, right. and see the coefficient 1 minus rho, that basically indicates when rho equals to 1, if rho equals to 1, then what happens? Then we can say that basically there is no lag dependent variable in this equation. So, simply we can say that delta yit implies delta yit, okay, equals to simply your beta xit plus uit. So, that means there is no presence of lag dependent variable in the model. So, the dynamism goes off, there is no dynamism in the system. So, if we want to have dynamism in the system, then the value of rho, the low should be less than 1, and that implies this model is delta yit equals to 1 minus rho into yi t minus 1 plus beta 2 xit plus uit, right. So, one thing we have to clearly keep in mind, since rho equals to 1 only gives the dynamic nature of this model, that is why this is called rho less than 1 indicates partial adjustment. So, it is not a fully adjustment model, right. If anything happens to my xit, that will result in a change in y, which will be partially adjusted, okay. Some part of the adjustment will happen in the next period also. That is the meaning of partial adjustment. So, we can easily understand this from this equation where we are saying yit minus 1, that means delta yit equals to basically 1 minus rho yit minus 1 plus beta 2 xit plus uit. So, this rho less than 1 indicates this model is basically a partial adjustment. You can now very well understand what does partial adjustment mean. Okay, rho equals to 1 is called fully adjustment model, and when it is fully adjusted, that means for any change in your explanatory variable, y changes itself in the same period. So, this change is not carrying over, is not getting carried over in the next period, there is no dynamism in the system. So, to have a dynamic panel data model, I must have rho less than 1, and that is why it is called partial adjustment. That is the reason dynamic panel data model is also known as a partial adjustment model, right. This was the thing we need to keep in mind. And then we have also discussed briefly in a model like yit equals to, when your model is this, let us say my model is this, then there are two sources of persistence over a period of time. The first persistence is due to the presence of this unobserved effect, which is ai, and why it is giving persistence, since yit is actually related to ai and ai does not have a t subscript, that means we can say that yit minus 1 is also related to ai. That means in each period, one of my explanatory variable, the lag dependent variable, is related to ai, and that is one source of persistence. So, that means in each period it is related, and since ai component is common in the error term, we can say that in successive periods ai is all your error terms are getting correlated and leading to a autocorrelation problem. Autocorrelation arises for another reason in this dynamic panel data model. Since yit is related to yit minus 1 and vit, then yit minus 1 is also related to vit minus 1. Same equation I can write for yit minus 1, right. So that means I can say that YIT is related to YIT minus 1 as well as VIT minus 1, and since YIT is correlated with VIT, so that means I can now easily say that VIT is also getting correlated with VIT minus 1 through the channel of YIT. That is also we discussed how the presence of lag dependent variable generates autocorrelation in the problem, right? And then we said that what is the solution? That means we cannot estimate this model by the OLS. We must go for the fixed effect transformation to remove the AI. But if you go for fixed effect transformation, then what we have discussed, YIT minus YI bar, what will happen, equals to my model is this. So AI will get cancelled out, and then what will happen, I will get, let us say, beta 1 YI t minus 1 minus YI dot minus 1 bar, and this is basically the mean value of the YIT minus 1 plus beta 2 XIT minus XI bar plus VIT minus VI bar. Okay. Then we said that this fixed effect transformation also does not work because this VI bar is nothing but 1 by T sum of VI T, that includes VIT minus 1. Okay. So, this VI bar includes VIT minus 1, and VIT minus 1 will be related to YIT minus 1, right, YIT minus 1. That is why this fixed effect transformation cannot rule out the correlation between one of your explanatory variable with the with this transformed error. At the same time, when you calculate the mean of YIT minus 1 bar, which is nothing but YI dot minus 1 bar, that also includes YIT minus 1, sorry, YIT, and that YIT would be correlated to this VIT, right. So, in both the cases, what we have established that VI bar is correlated with YIT minus 1 because VI bar includes VIT minus 1. Okay, VI bar includes VIT minus 1, that is why that is correlated with YIT minus 1. Similarly, we have also said that this YI dot minus 1 bar includes YIT, and that itself will get correlated with VIT. So, fixed effect transformation cannot rule out the correlation between these two. That is why fixed effect transformation is not applicable. So, then what is the solution? Then we have discussed, so when fixed effect transformation is not applicable to estimate this type of dynamic panel data model, we can actually go for, so neither OLS nor fixed effect actually is applicable. Straightforward OLS application is not possible, fixed effect transformation is also not applicable. Both of them will lead to a bias and inconsistent estimate. So, OLS and OLS application in the original equation and FE transformation will lead to biased and inconsistent estimates. Okay. and that bias we discussed, that is called nickel bias, NICKELL, nickel bias, which is of order 1 by T. Okay. So, we cannot apply OLS and fixed effect transformation because both of them will lead to some kind of bias, and that bias is known as nickel bias because nickel was the first econometrician to introduce this type of bias, which is of order T. That means for a small sample this bias would be a great amount, and we also said that even when T equals to 30, that bias is amounted to at most almost 20% of your original estimates, right. So, when fixed effect transformation and OLS does not work, then what is the solution available? So, we may go for the first differencing. So, if we go for first differencing, basically that means YIT minus YI T minus 1 equals to beta 1 yi T minus 1 minus yi T minus 2 plus beta 2 xit minus xi T minus 1 plus ai will get cancelled out, and then I will get VIT minus VIT minus 1, right. And once again we can say that this YIT minus 1 is correlated with VIT minus 1. So, that means this is correlated with the error term. So, again first differencing is also not able to solve the problem of endogeneity because my variable, one of my explanatory variable is getting correlated with the error term. Now, that much we have discussed in our previous discussion. So, what is the solution then? The standard solution is basically the utilization of instruments. As we all know, when to solve endogeneity problem, when you have some of your explanatory variable is correlated with the error term, then what is the use? What is the solution? Solution is to use the instrument, okay. And this particular idea first was given by two famous econometricians, Anderson and Hsieh. Anderson and Hsieh. In short, AH approach. Okay. Anderson and Hsieh. So, what they say that basically that means this model turns out to be delta YIT equals to beta 1 delta YI T minus 1 plus beta 2 delta XIT plus delta VIT. So, when correlation between delta YI T minus 1 and delta VIT is not equals to 0, then the idea is we need to use instruments for this delta YIT minus 1. And what are the instruments for delta YIT minus 1? YI T minus 1, they say that we can use two instruments, okay, two types of instruments basically based on an Anderson Hsieh. They say that you can use either second lag of the undifferenced variable, that means yi t minus 1 or delta yi t minus 2. Okay. Second lag of the level or second lag of the difference, both of them can be used as IV for this delta yit minus 1. Okay. That is the idea given by Anderson and Hsieh. So, in this case, if we use this, let us assume that we are using yit minus 2, that means second lag of the level variable we are using as instrument, and then in the Anderson and Hsieh approach, my instrument matrix will look like this. So, this will be yi 1 yi 1 yi t minus 2. Okay. So, this is basically the instrument. So, that means the first observation is lost for the second period. So, this is basically t equals to 2. So, what is the observation? Now, this is for third period when t equals to 3, and this is the tth period capital T. Okay. So, the first row of this instrument matrix, the first row indicates second period, and that observation is lost. So, we need to remove that observation for each panel, and that will lead to, so what I will say that first row of the Z matrix indicates second period. And the first observation is lost for each panel. Okay, and this implies a reduction in sample length. Okay, reduction in sample length. So, first observation is lost for each panel when your Z matrix is like this. So, what we are doing based on the idea given by Anderson and Hsieh, we are taking yit minus 2 as the instrument. So, that means the first observation is available only from third period to be used in the regression. And if we include third period also, if we include yi t minus 3 as an additional instrument, then Z will become like the following. So, what will be the Z matrix then? So, this will be simply Z will become then, so this is yi 1, the first case was yi t minus 2, and when you use the third lag also as additional instrument, we will lose one more observation, and then this will become yi t minus 3, right. So, that means this is for t equals to 2, this is for t equals to 3. So, this is for t equals to 3, and this is called t equals to 4. So, that means I lost 2 observations if we include third lag also as an additional instrument. So, that means here what is happening, in the previous Z matrix I was using only second lag. So, that means using second lag means I am using only one orthogonality conditions, and when we are using third period lag also as an additional instrument, my Z matrix looks like this, and as a result of which what is happening, I am getting more instruments, more orthogonality conditions, but at the same time I am having less number of observations available for my estimation. So, that means there is a trade off between what you can write, that means, which implies, so there is a trade off between lag length and sample length. Lag length and sample length. If we use only yi t minus 2 as an instrument, then my lag length is only t equals to 2. So, that means I have preserved sample length, sample is not getting reduced, but lag length is only 2. So, that means I am using one single orthogonality condition, I am not utilizing all the available information available in the system, and the moment I include additional instrument as yi t minus 3, then I am losing 2 observations for each panel. Okay. So, this basically says that there is a trade off between lag length and sample length. And to avoid this problem, to avoid this lag length and sample length, to avoid this trade off between lag length and sample length, Holjiakin et al. Holjiakin et al. What they suggested, that instead of using many more lag as instruments, why not using only one instrument YIT minus 2 for each period, second lag of the untransformed variable as instrument for each period, and replace all these missing observations by 0. Okay? So, that means suggested that using second lag of YIT as instrument, as only instrument for each period and put 0 for all missing observations.